So we just finished the numbering systems, decimal, binary, octal, and hexadecimal. We're going to talk about converting hexadecimal to binary. If you can, since we know how to convert each single one into decimal already, which was mentioned in each of the videos, we will now be able to convert from hexadecimal to binary easily and binary to hexadecimal. And that's why a lot of times computers, you'll see representations of the binary code underneath in a hexadecimal format. So let's give us a random number. We'll do that. So this here, you can convert this into hexadecimal without actually having to know the value underneath, right? The total value. And that is why we separated it into these 4 bits each, right? Which in computers this is actually called a nibble, right? If you get 8 bits is a byte, 4 bits is a nibble. It's funny that it's that, but that's actually what it is. So there's probably a joke behind it or something, I don't know. But if you actually look at it, we can now, this representation here actually aligns perfectly with hexadecimal, right? And that is because if you look at it, with these 4 bits in decimal, you can represent 15, a total of 15 in binary. So you say, what do you mean? Well, let's look at this, right? Let's take this, what we learned, we'll take binary, right? And we'll say that the first column that you're going to see when you have 4 digits, right, is going to be a 1's column, a 2's column, a 4's column, and an 8's column. So n times 8 in the first column, n times 4 in the second column, n times 2 in the third column, n times 1 in the fourth column. Okay, so this in binary, so this first number right here, 1001, if we want to convert it, we put a 1 here, and then we have a column, and we have a 0 and a column, and a 0 and a column, and a 1. And we add that up, right? And we know that that is 9. Equals 9. Double equal, sorry, that's a programming thing. We're not trying to set a value, we're trying to compare a value. So 1001 equals 9 in decimal, correct? Yes. So I want to convert this into hexadecimal, though. How would I do that? Well, 9 in hexadecimal is 9, right? So nothing changed between in hex. 9, because we have a 9, is equal to 9 in decimal. There's no difference in that. But what happens when we get into something that's bigger than decimal, right? And let's go to this next one, 1101. Would be our next column. So we'll go ahead and do 1, 1, 0, 1 equals, and we'll go through and we'll say 8 plus 4 plus 1. So that's 13, right? So 8, 4, and 1 is 13. So that equals 13, right? Well, we don't have a 13 in hexadecimal, do we? But we do have A, which is 10, 11, 12, 13. So D. So 13 equals D. And that right there, you can go through, and right now we're doing an extra step, right? We're taking, we're converting it first to decimal, then we're taking the decimal and we're converting to hexadecimal. We don't have to do that, right? We can actually, we know that in each 4 bits of binary, you can show a single digit of hexadecimal, or a single character of hexadecimal, I should say. So when you have 4 bits, the highest you can get is 15, which if you don't remember, so if we look, 1, 1, 1, 1. 1 times 8, 1 times 4, 1 times 2, 1 times 1, add them all together, you get 15. So 8, 4, 2, and 1 added together equals 15, which means that hexadecimal, for some reason, when these are all on, you just get F, right? So you can convert directly to it if you break these up into bits. So I can go through and I can do this entire number, right? In my head, I can convert to hexadecimal, and it will equal the same underlying value in decimal. So 1001 is 9. 1101 is 13, so we need a D. We have 1110, which is 12, 14, 14 would be E. And then we have the final one, which is a 4 and a 2, which is 6. So 0x. And I was doing that, I wasn't really following along, just so I could show you, like, this is all you can do in your head once you get the numbering systems down. So 1001, 1101, 1110, 0110 equals. So 9DE6 equals this, and this was done without converting to decimal first, right? And if we want to check, we can actually check and see, just to make sure I'm not lying to you. We'll open up the programmer, the calculator. If you go into calculator on Windows and you go to programmer, you can do that, and you can see, then you can type in here based on what you want to type in. So let's say I wanted to type in the binary that we just did. Now I will type in, we're going to go start here, so 1001 1101 111 which, if you look, it gives you 9DE6, right, which is the same underlying value. So 9DE6 is what we just did. And you can do that all in your head by strictly just 15, breaking up the digits in binary, the representations, and into 4 bits each. So take 4 ones or zeros, put them in one, truncate 4, 4, 4, and you can convert directly into binary, or directly into hexadecimal. My apologies. But yeah, like, and the same goes backwards, right? So let's say I have, I'm going to create a random hex. So if you notice I did this x0, I could actually do this 0x. Yeah. That's what you would see once again, like when you're looking at a disassembly or something like that. You'll see this, the hex representations normally. I know you can change it, like in GDB, you can, if you're debugging something, you can change like overall what you want it to show in, but majority of the time the standard is hexadecimal is what you're going to see. So let's convert that back into binary. Let's convert something into binary. So let's just make up a random number, C. Actually, let's do dead beef. This is funny because, so dead beef is something you'll see if you're doing exploits. People, a lot of like proof of concepts, when they do exploits, will write in dead beef to the registers to just pwn stuff, right? The reason it's done is because this is all, if you've noticed, all these digits here, or all of these representations, are all a hexadecimal valid, right? So you can DEAD BEEF is all valid. DEAD BEEF it's all valid in hexadecimal. So this, we take dead beef, and it's also 8-bit aligned. It's also 32-bit aligned, which is good, right? Like the 32-bit aligned is if you take these 8 digits and you take these 8 letters or representations, and you multiply them, that they're each 4 behind. 8 times 4 is 32. So yeah, that's where you would get that from. So 8 times 4 is 32. This represents something that can get pushed into a register quite easily. You don't really, you notice when it's in there. I'm kind of going off on that, so I'll stop talking about exploitation. But if you ever see dead beef when you're looking through like exploits or vulnerabilities and stuff, note that is why, is because it is aligned to a 32-bit system, and it's all valid hexadecimal characters. So we will move on to converting this back. So all we're going to do is we're going to do four bits in each column and space out, and then just move back, and you'll see that it's going to equal the same thing, right? So we know that D is actually 13, right? So 13 is 1101, right? That's 13 because we do 8, 4, 2, and 1. 8 plus 4 is 12, plus 1 is 13. So 13, E would be 14 then, so that would mean that it would be 1 less than 15. Then we have A, which is 10, so 10 would be, we need an 8, we need a 0 for the 4, and a 1 and a 0, and then we need another D, which is 0, 1. Take a B, which is going to be 1, 0, 1, 1. E, which would be 1, 1, or sorry, yeah. E, which is 8, 4, yeah. Yes, okay, yeah, 1, 1, 1, 0. And then another E, and then an F, which is all ones. So, dead beef is this in binary. At least it should be. We're about to find out, right? We're going to go to the calculator, and we are going to type in 1101, 1110, 10. Oh, I'm typing that into hex still, which was giving us a huge number. Don't do that. 1101, 1110, 1010, 01, 1011, 1110, 1110, 1111. And as you can see here, we got dead beef. So it converts perfectly, right, into it. And that's a reason why you'll see so many hex representations of binary numbers on computers. I might have lost a few people. You guys probably don't care that much about going in depth, but like those are little things that like you'll see, right? Like you might go look at videos on exploitation online, and you'll see that they say dead beef in there. It's like, why do you use dead beef? Well, that's because it's 32-bit aligned. It fits perfectly, and you don't care about the binary representation underneath it, but those are all valid characters in hexadecimal. So we went from decimal to hexadecimal, we went hexadecimal back to decimal, or we went from, confusing decimal and binary, my words. It's early and I still am drinking my coffee. But binary to hexadecimal, and we went from hexadecimal back to binary. And in between we did do decimal as well. So let me know if you guys have any more questions below. I do apologize for, like I said, I mixed up. There's probably a few times in this video that I meant to say binary instead of decimal, but hopefully you guys get like the actual underlying reason why these representations map to the values underneath them. Next up, we'll talk about protocols.